Hello, I'm Dylan Ocala, and today I will be presenting joint research carried out at the University of New Hampshire with my master's advisor, Wheeler Ruml, on the topic of concurrent planning and acting. Namely, when to plan and when to act when the two are allowed to run concurrently. Now, there's two traditional approaches to this problem. The first, offline planning, the agent remains at the start state planning a complete solution before ever executing even a single action. And there's sort of an implied property of the start state in this case, which we refer to as an identity action, which allows the agent to remain at the start state without the world changing around it and invalidating its current knowledge base. The second approach is real-time planning, in which the agent does not use one of these identity actions even once, and instead plans incrementally using the time while one given action is executing to plan for subsequent actions. Now, there's a number of questions we want to address, including how can we choose an appropriate strategy? Is there some middle ground between the two? And can we choose to plan and commit dynamically? And most importantly, how can we decide what to do in a principled way? And the approach that we use to address these problems is meta-reasoning. The problem setting that we are working in, we're planning outward from the agent's current location towards some goal through the state space guided by some heuristic. And our objective is to minimize goal achievement time, or GAT for short, which is simply the time taken from the start of planning to the execution of the final action. We assume that we have access to some inadmissible cost-to-go heuristic Hhat and respective total solution cost heuristic Fhat, which can be computed either prior to search or, as we do in our research, online. And for simplicity's sake, we're only dealing with known deterministic worlds and a serial plan. Now, our algorithm, MoRTS, addresses this problem setting by considering two core decisions. First, if we have an identity action immediately applicable, and we have two immediately applicable actions, alpha and beta, where alpha appears to be the better of the two according to our heuristic estimate, should we simply emit alpha now, or should we instead emit an identity action and use the time to deliberate further and determine whether or not alpha is in fact better than beta as we believe it to be? Second, if we do commit to alpha, should we commit just to alpha, or should we commit all the way to the frontier under alpha, or should we cut short at some point along the path at some prefix? Now, to make this decision, we follow a simple principle in meta-reasoning. We want to plan when it appears worthwhile. So we want to plan only when the expected goal achievement reduction outweighs planning time. So goal achievement time reduction depends on whether f of alpha is actually worse than f of beta, and if so, by how much. More precisely, if we have some outcome of alpha and some outcome of beta, x alpha and x beta representing f hat values after search, we say the benefit of that particular outcome is equal to 0 if alpha winds up being better than beta, because naturally we would have taken alpha regardless of whether we did more search. And we say that if beta is better than alpha, benefit is equal to the difference in those resulting Fhat values. Now, if we have some probability function here, then we can compute the global expected benefit of search as for every outcome of alpha and every outcome of beta, the benefit of that outcome weighted by its probability. Now, that is assuming we have such a probability function, but how do we get one? So, as I said, we have this inadmissible heuristic value that we call Fhat. And because that is our unbiased heuristic estimate, it is presumably the closest estimate we have to the true value of F star. So we make an assumption that F star lies normally distributed around F hat. Now, since F is our admissible heuristic, we know that F star can't possibly be less than F, and so we use this difference to bound our normal distribution. Now, that's assuming that we search all the way to the goal. If we perform no additional search, then we expect F hat to remain exactly where it is. Likewise, if we perform some intermediate amount of search, which does not reach all the way to the goal, we expect our belief about the future value of F hat to be somewhere in between these two distributions. So that's all describing this in the context of the identity action decision. But it still applies to the path prefixing decision. We simply look at each node along the path from alpha to the frontier, and we stop at the first point where planning is preferred according to that benefit equation I just presented. Now, in order to evaluate the performance of our algorithm, we tested on a number of both small and large benchmarks. Here, I'm going to present a number of small, handcrafted, two-dimensional grid nav instances. These are simply caricatures. There are details and dimensions in the paper. The first we call cups. It's simply a series of nested U-shaped corridors. A star handles this quite well because it is only required to expand each state at most once, whereas real-time searches will find themselves misled by the heuristic, and they'll be forced to do learning in each of these cups in order to get out and eventually reach the goal. As you'll see in the results here, A star does outperform all of its competitors in terms of goal achievement time here. However, while the real-time approaches have goal achievement times in the thousands, MoRTS is a full order of magnitude better and does almost as well as A star. Next, we have the slalom instance, which consists of a long winding path, which a greedy algorithm would follow the heuristic down, as well as two straight shots on either side, which are actually part of the optimal path to the goal. Now, A star, once again, outperforms the real-time approaches. However, MoRTS is able to use deliberation in order to avoid getting caught in the trick of this long winding path, and in fact outperforms all of its competitors, ultimately taking the straight shot down the side of the map. Finally, we have the uniform instance, which is simply a uniform field of obstacles which don't do much to confuse the real-time searches, as you'll see here. However, A star is forced to expand a large number of states before it even begins to execute its solution, even though it finds the optimal solution. Whereas the real-time approaches in MoRTS are able to follow nearly a straight shot directly to the goal. In short, MoRTS is able to use deliberation in order to adaptively decide between offline and real-time like behavior. Next, we had a number of larger benchmarks, two of which I present here. First, in order to understand these plots, my x-axis here is labeled as expansions per unit duration. What that is the simulated duration of a given action execution. So on the left here, effectively, search is expensive, and on the right here, search is cheap relative to the time taken to execute a single action. On the y-axis, it's simply the log 10 factor of optimal goal achievement time. In short, the lower you are on the y-axis, the better your goal achievement time. So the first domain here is the classic sliding tiles puzzle, specifically the 15 puzzle. And as you'll see on the left here, when search is expensive and Fhat actually outperforms its competitors, MoRTS is able to perform roughly on par. On the right here, where search is cheap and A star does well, MoRTS once again does well. And in between, MoRTS adapts between the two in order to dominate its competition. Next, we have the traffic domain, which is a two-dimensional grid navigation problem where the agent is trying to find its way across some map through a series of moving obstacles. And once again, you'll see, even though there are no identity actions in this domain, MoRTS is able to leverage the path prefixing decision in order to outperform its competitors. In summation, this is part of an ongoing objective to minimize goal achievement time. There's been work done by the University of New Hampshire AI group in the past in the context of the Bugsy algorithm, which is an offline approach to this problem. And as I've just presented, MoRTS, which is dealing with concurrent planning and acting. Our approach uses meta-reasoning, which we believe follows a beautiful principle. And as you've seen by my presentation, and maybe even through the paper, provides state-of-the-art results in practice. There's a number of possible extensions which we believe would be interesting for future avenues of research, including applying this logic to non-deterministic and partially known settings, and also the application of not quite identity actions. So in the event that an identity action is not available in a domain or at a particular state of a domain, the algorithm might be able to achieve many of the same benefits. In short, we've addressed one of the core tensions in concurrent planning and acting, namely when to plan and when to commit. Thank you.